back to another one of our A-level maths, in this case mechanics videos. So today we're going to be looking at the final major section of mechanics for AS anyways, which is the pulleys and kind of F equals MA, and we're going to lump that together. We're actually going to do a little bit of friction as well. So I'm going to use this first question as like a demonstration in order to fully teach you exactly what's happening. So with pulleys, so I'll just write A, first of all we start with a few kind of assumptions. Okay, so in this case we have two masses, 2 kilos and m kilograms, where m has to be less than 2. The particles are connected by a light inextensible string. So first of all, think about what that means. When something is light, all that means, in mechanics anyway, is that it has no mass. So the reason why that's important is that we don't have to draw an arrow for the weight of the string that it's connected by, and it also means that it doesn't have any kind of reaction force with the pulley. Really important. And inextensible means that it doesn't stretch, okay, which might be a bit obvious. So the actual effect of this is a bit more interesting. So when the string is inextensible, what does that mean? Well, it means that both of these masses are going to move at the exact same time, not the same and the same rate as well. Okay, because if you think about it, it's like they're being held by a rod, if you like to think. So either side of this pen, right? If I push one side, the other side instantaneously moves. Okay, so all that means is, in this case, there is no delay in acceleration. No delay in acceleration, but also that they move at the same acceleration. So masses move with the same acceleration. Masses move with the same acceleration. So both of those are really, really important facts. And then the last one, it says a smooth fixed pulley. So smooth just means that there's no friction between the string itself and the pulley, which again is an important kind of assumption for us to make, because it means that they're again going to accelerate at the same rate. Because if there was some energy lost with the acceleration, then that would cause some issues. The object falling down would actually fall with a higher acceleration than the one being pulled up. And the fixed pulley just means the pulley isn't going to move, which again, fairly useful. Okay, the first thing it says is that A is initially 3 meters above the ground. So we can do this. We say that this height here is 3 meters, where this is the actual floor. Okay, and the string is released from rest with the string taut. Taut just means there's no slack in it. So again, this just means that we're going to have instantaneous acceleration. And the hanging parts of the string are vertical. After A has been descending for 2.5 seconds, it strikes the ground. Particle A reaches the ground before particle B reaches the pulley. So with questions like this, it's really important that they give you this piece of information. If they don't give you this piece of information, generally speaking, part C will have like an assumption, and you have to talk about how the assumption affects your answer. This line here is really, really important, because if you think about it, if B hits the pulley before A reaches the ground, then that means A will never reach the ground. They're both going to stop, right? So that's all that means there. But there was a question before where they didn't mention this, and so one of the assumptions was that the actual mass B did not touch the pulley before A reached the ground. Okay, so after A has been descending for 2.5 seconds, it strikes the ground. Show that the acceleration as it descends is 0.96 meters per second squared. And hopefully it makes sense that the acceleration is going to be downwards on this side and upwards on this side. So this is the kind of interesting thing about pulleys, is that we actually have acceleration in 2 different directions depending on which side of the mass that we take, right? So A is going to be accelerating downwards because it has mass, and it tells us. And B is going to be accelerating upwards because A is heavier than B, right? That's what it means by the m is less than 2. Right? Hopefully that makes sense, right? It makes logical sense. So part A is actually just to solve that question, because with pulleys, we can actually treat them as completely separate entities. So what I mean by that is we can just look at A side. So we can say for A, and I'd recommend writing this in your actual working out so that the examiners can give you marks, because they'll understand what you're doing a bit better. But we can actually treat this whole thing as completely ignoring B side. So effectively, I'm just looking at a mass of 2 kilograms That's accelerating downwards, like that. I don't have to worry about anything else. And it's in free fall, right? Well, not in free fall exactly, but it's just accelerating constantly. So the S in this case is going to be 3 meters because it says it moves 3 meters before hitting the ground. U is 0 because it says that it's released from rest. V is don't know. Acceleration is don't know because, again, it's not free fall exactly. And the reason for that is this mass here is actually slowing the object down. Okay? And time is going to be 2.5 seconds. And then all we're using is classic SUVAT in order to work this out. So we have S, U, and T, and we want A. So that means there's going to be S is equal to UT plus a half AT squared. U is 0, so we don't have to worry about that at all. And this becomes quite an easy equation to rearrange for A. It's just going to be S, 2S over T squared equals A. So that means A is just going to equal, and then all we have to do is get our calculators up. So it's going to be 2 times the distance, so that's 6 over T squared, which is 2.5 all squared. And we should get an answer of 0.96. So you're very lucky in these kinds of questions because the examiners are being somewhat reasonable, because what they're going to do is actually give you what the answers are. And you'll notice this with a lot of more recent mechanics questions. They give you the answers in the sense that it would be a show that question. The reason why they do that is they want to do something called error carried forward. So if I didn't know how to do part A, I can do part B and assume that the acceleration is 0.96, and I can get full marks in part B and C. So that's quite important there. So with part B, I'm actually going to redraw. I'm actually going to use this diagram, but I'm going to redraw it, okay? So what we're going to do is that's my pulley. Again, please forgive the drawing. It's not going to be perfect, but, you know, you guys know that by now. The reason why I'm redrawing it is because there are some forces that are missing, okay? So first things first, we have mg on this side. Right? It's accelerating upwards, and we already know what the acceleration is. It's 0.96. However, right, and this is the key thing, is this mass is pulling the string down, right? Even though it's being pulled up. The thing providing that upwards force is tension. Okay. Likewise, on the other side, the mass of this was, I can't quite remember, it was 2 kilograms, so this would be 2g, because that's the weight force, right? Remember, weight is just equal to mg. Okay. That's also going to have a tension pointing upwards, which is slowing down the acceleration. Okay. And these tensions are both the same. Why are they the same? Well, it's because we have that the string is light and there's no friction. Okay, so these assumptions here all effectively mean that they have the same acceleration and the same tension, which is nice and easy. And then what you're going to do is, and we also have acceleration down here, so let's draw that. And now here's where things get a bit more interesting. Generally speaking, you're actually going to do simultaneous equations for the second part, which should make sense. It's 7 marks. It's not going to be the easiest thing in the world. So what you're going to do is you're going to resolve it for A and B. So for A, I'm going to take downwards as positive, and we're going to use the equation F is equal to ma, which we have done a video on previously, but this just means that the resultant force is equal to mass times acceleration. So since I'm taking downwards as positive for A, we're going to have 2g minus the tension is equal to 2 times A, which is 0.96. Okay. Now, we can work out the tension from here, right? We have 2g minus t, so we could swap this around, and we're going to have 2g minus 2 times 0.96 equals t. Okay? Nice and easy. So all we need to do now is actually work out what on earth that value is. It could be an idea to actually work it out right at the end, but it'll be fine. As long as we keep a relatively decent number of significant figures, we should be completely A-okay. And we get, oh, there we go, we get 17.7, nice, easy number to work with. Okay, nice and easy. Already got marks. Now for B, we're going to take upwards as positive. So it doesn't actually matter which way round you take as positive, so long as you make sure all of your vectors match. So for example, if I took upwards as positive for A, I would have to make this minus 2g, this plus t, and this minus 0.96, and I'll get the exact same answer. Okay, except it might be negative, for example. But that's totally fine because it's a vector, right? It should have a direction. So I always take the direction of acceleration as positive, because acceleration is the one that people tend to forget has a sign. So if you take acceleration as positive always, you never have to remember that. So over here we have t minus mg. And I'm going to sub in t in a second, but I like to just keep it nice and simple for now. Times 0.96. So t minus mg, let's work this out. In fact, we could just move mg over to the other side. So we have t is equal to 0.96 m plus mg. So if I factorize out the m now, we have t is equal to m 0.96 plus g. So m is equal to t over 0.96 plus g. We know what all of those values are, but I'm going to sub them in just so you are fine with seeing it. And I gave myself the perfect amount of space. That's perfect. Okay. So let's have a look. We have 17.7 over 0.96 plus 9.1. And we get 1.64. And if you look at the answer, show that the mass is 1.64 kilograms. So 1.64 kg to 3 significant figures. And that's 7 marks. In my opinion, it's not that long. This is why I like mechanics as a topic. A, it's very logical. Once you've done a bit of practice, you'll be able to get every single question correct, which is really, really nice. You don't have to remember stuff like with stats and pure. So, for example, with pure, you have to remember all the integration and differentiations, like what they become. You have to remember a bunch of trig identities and all this other stuff, and equations too. With mechanics, there aren't really many equations you have to remember. It's suvat, and then F equals ma, and then there's one more, which is for friction, and that's it, right? Which, you know, in total, that's what, 6, 7 equations? Not too bad. And you get a lot of marks for not much. Like, this is 7 marks, right? It's really not that much. For part C, and this is very common for mechanics questions, especially when we have diagrams and things like that, it will say, how have you used the information? What assumption have you used? How can we make it more accurate, you know? That's the kind of thing they look for. So say how you've used the information that the string is inextensible. As you mentioned before, masses move with the same acceleration. So what we're going to say here is the masses have the same acceleration, or they move with the same acceleration. So the masses move with the same acceleration. There we go. And that's not too bad, hopefully. So again, pulleys don't always have to be vertical. They can be horizontal and vertical, but the same thing applies, okay? However, there is something that's actually a bit nicer with this, is that the direction of acceleration should be very, very obvious. I'm not even reading the question yet, and yet this has to be accelerating downwards, and this has to be going to the right. Because, I mean, think about it, right? It would be really weird if you had something on a table and there's something hanging over the edge and the thing on the table just magically started lifting it up, right? That doesn't happen in real life. So when you have situations like this where things are hanging off a table, it's always going to be the same. The thing hanging off the edge is going to be accelerating downwards, and the thing on the side is always going to be accelerating to the right. So we have a particle of mass at 5 kilograms, so let's start adding to this diagram. We have 5g here. Rests on a smooth horizontal table. So smooth, again, means no friction. Particle A is attached to one end of a light and extensible string. We've discussed that before. Smooth pulley, cool. And mass of 4 kilograms, so we can make this 4g. Which hangs freely below the pulley, 1.4 meters. So again, we can just do this whole thing of 1.4 meters. System's released from rest. Particle A does not touch the pulley. Okay, cool. The other thing we can do is actually add the tension lines. So the tension should be up for this guy and to the right for this guy. Because again, the tension is what's dragging the object along. Part A, it says find the tension in the string before B hits the ground, because when it hits the ground there's obviously no tension. So what we can do here is we can resolve for A and B. Now you might notice something interesting with A. And we're going to take to the right as positive. So again, F equals ma. This is a very useful equation. There's only one force, right? It's just T is equal to 5A. So how comes? Why do we not include this? Well, we always have to consider that forces that act perpendicularly to each other are completely independent. Okay? So that this 5g going downwards has no effect on the actual acceleration to the right. None at all. Okay? So, we completely ignore it. When I resolve taking to the right, which is what I'm doing here, I'm only looking at forces going along that direction. So right and left. Up and down does nothing for me, okay? I'm only looking at the things going right and left. In this case, 5g is not going right or left. So that's it, and that's all we can really do for the tension, right? So we have T equals 5A. I don't know what A is, and I don't know what T is. So I can't really do anything else. So if you ever do this, and this is a bit of advice for all mechanics questions that look like this, resolve both things and in all directions, and you'll find an answer, guaranteed, okay? So since I don't know what else I can do there, I'm going to resolve B now, because that's the only kind of move I've got left. Downwards we have 4G, right? Because again we're using F equals ma. Upwards we have tension, and that equals 4A. Okay, so I'm looking at this and I'm like, okay, what can I do? Well, I can now substitute in for whatever I like. So in the question, it says find the tension. So it makes sense to not cancel the tension out from my answer. So instead I'm going to rearrange this equation for A. Now, again, technically speaking, you could find what A is and then also find T, because I'm willing to bet we need to know what A is for the next part. So either way round, you're not actually wasting any time, because if you find out A in this part, you can use it in part B, right? We're going to need acceleration eventually, just because I'm willing to bet we need to from the time taken. But what we'll do is we'll do it in kind of order in this case. So A is equal to T over 5, so that means this thing here becomes 4G minus T equals 4 T over 5. So if we add T to both sides, we get 4G is equal to, that would be 4 T over 5, add another 5 over 5 would be 9 T over 5. So that means T is just equal to 5 times 4G over 9. The way I got that is I've times both sides by 5. I didn't kind of simplify 5 times 4 to 20G because I thought it might be a bit confusing. So I've times both sides by 5 divided by 9. And now I can actually work out what that is. In this case, if you notice, they don't tell me what the tension should be. This is because it's an older question. So in the older questions, you won't, unfortunately, be able to get what the answer is in a lot of them, which I think is a bit silly. I much prefer it the way it is now, but that's what it is. 21.8 newtons. Cool. There we go. 4 marks, and in my opinion, it's really not that quick. In real life, I guess, in your test, you'll probably be able to do this in about a minute. So it's really, really efficient, but don't rush, okay? I've taken my time, but it didn't take me 4 minutes to do that question. They give me 4 minutes. Now it says find the time taken for B to hit the ground. Okay, so let's set up our SUVAT for now, right? So I know that S from the question is 1.4. U is 0 because it tells me in the question that it's released from rest. Okay. V is no idea. A is, I'm not going to write question mark because we don't know what it is. And T is what we want to work out. Now, here's a quick tip. S, U, and T, there is no way I can work out what T is, okay? All of the equations that we use require at least 3 things to work out a 4th thing, okay? So you need to have 3 variables. So I need to work out what A is. Well, A is just T over 5, right? So if I work what that is out, so A is equal to 21.8 over 5, I can now work out my answer. which is 4.36 meters per second squared. So let's do 4.36. And now I can actually work out what t is. We have s, u, a, and t. So we can use s is ut plus half at squared. Again, with free fall, we use this a lot. So it's kind of, should be used to this one. U is 0, so that whole first term is going to be 0. Now we're just rearranging for t. So t is just equal to 2s over a square rooted. That is correct. God, I don't know why I had to struggle with that for so long. So that's 2 times 1.4 over 4.36. So we've got square root, 2 times 1.4, that's just going to be 2.8 over answer. 0.8 seconds. So we can do it to two significant figures, 0.801 seconds. That's just a 3SF. Okay, perfect. Technically speaking, we should do it to 0.80 to 2SF. And the reason for that is if we look at the numbers we get given up here, the lowest number of significant figures is 2. So our answer should be given to two significant figures if nothing is specified. So that's just a bit of a tip. They're a bit more lenient than they used to be, so we don't have to worry too much. But any of you that do physics will know to do that as well. In physics, you do actually need to round it to the correct number of significant figures, especially on paper 3. Anyways, here we go. We have the other type of pulley question, which, well, I'm going to draw it out for you. We have a car of mass 750 kilograms. So I'm going to draw my car as a box. Yeah. 750G. And it's pulling a trailer of mass 300 grams. 300G. Okay, and it's connected by a light tow bar. Now, ignore how long the tow bar is. I just need a lot of space to do stuff. And, okay, let's keep going. Horizontal resistances of the car and trailer have magnitude of 250 and 100. Okay, so the resistive force is probably like air resistance, for example, is going to be here. That is 250 newtons. And for the trailer, it's going to be 100 newtons. Okay, the engine of the car produces a constant driving force of 1600 newtons. And we should keep in mind that there is going to be a tension for both these guys. Now, this may look very weird, right? That the tow bar is producing two tensions. Well, it's actually not. Tension is a force that keeps something held together, right? So if I actually grab something and I pull it apart, there is a tension that's acting this way to stop my hand pulling it this way, and there's a tension acting this way to stop my hand pulling it this way. Okay? So there are two tensions. It's one force, right? So the actual value is going to be the same. In general, everything we do in mechanics, especially with maths, if it's one object, the tension is the same throughout. So this tension will be equal to this tension here in terms of magnitude, so in terms of actual size. Okay, so it says find the acceleration of the car and trailer. So something that's quite interesting and quite useful is that when you have a system that's operating in the same direction, the same plane, we can treat it as one big system. The reason why this is useful is I don't know what the tension is, and I also don't know what the acceleration is. And the problem is I'll have two unknowns, which means I'll need two equations, which is a pain in the backside. So instead, I'm going to treat this as one system. So I'm going to write a whole system. Now, you don't have to do this next part, but I'm going to do it just for those of you that have never seen this before, right? If I treat this as a whole system, what that means is I have one object which has a weight of 1050 G, right? It has a driving force of 1600 newtons, and it has a total resistive force of 350 newtons. Let me just go through and tell you where I got these numbers from. This weight is the combined weight of both of these objects, so 750 plus 300. The driving force is the driving force, 1600 newtons. I should probably put newtons here as well. And this 350 is from the combined resistive forces. And this means I don't need to take into account the tension, which means I only have one unknown, which is really, really useful considering I just want to work out the acceleration. Okay, so I can use F equals ma now, and my life is much easier. Okay, so F is going to be 1,600, because I'm taking to the right as positive again, perhaps I should have indicated that, minus 350 equals 1050A. So that means A is just equal to 1,600 minus 350 over 1050. Okie dokie. So let's put it on. Minus 350 over 1050 gives me 25 over 21, which is 1.19 meters per second squared. And there you go, 3 marks. Not too bad, right? I don't think that's too bad for 3 marks. And then part B asked us to find what the actual tension is. So the tension, you can just take either one of these guys as what you're resolving for. So you can resolve for the trailer or the actual car. So I would prefer the trailer, and the only reason why is that there's fewer numbers. That's literally it. So if I resolve specifically for the trailer, then I'm going to use F equals ma, and again I'm taking to the right as positive. I have tension minus 100 is equal to the mass just of the trailer, 300, times 1.19. So now tension is equal to 300 times 1.19 plus 100. Now I sub it all in and I get my value. So 300 times 1.19 and then add on another 100 for fun. And you get 457 newtons. So actually, I'm just going to put it on brackets again just to make sure I didn't do something stupid. Yeah, 457 is fine. And that's another 3 marks. I mean, that, in my opinion, is really, really generous. Okay, so here we have another paragraph, whoop-de-doo. So, and it's also a 7 marker, so I'm actually going to do it up here, just so I can read whilst I'm writing this down, otherwise I'm going to go crazy. The car is moving along the road. When the driver sees a hazard ahead, he reduces the force produced by the engine to 0, so this becomes 0, and applies the brakes. The brakes produce a thing of blah, 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 given the resistance changed. Find the value of F. Okay, so this is an entirely different new situation, so let's go through it. So we have, boom, all of this stays the same. I probably should have drawn this a bit bigger, but oh well. Obviously the masses stay the same, because there's no reason for the masses to change. The resistances stay the same, which is actually a pretty bad assumption if you think about it. The tension, I can't read. The thrust and the tow bar. So the thrust bit is a bit more interesting. Thrust is the opposite of tension. So if you notice over here, our tension was going to the right and then to the left. But think about what's happening. In that situation, the bar is being pulled. In this situation, it's being compressed. And we call that force thrust because it acts in the complete opposite direction. So this is actually going to go this way and this way. So that is very different to what it was before. It's the opposite in terms of very different. Okay, and the acceleration logically should be this way because it's slowing down, right? It'd be weird if you pushed your brakes and you started accelerating forwards. That would be a bit of a disaster. And is that all the information? The brakes produce a constant force F, so now we need to just put F here. And that should act on the car itself. Cool. Given that the resistances are unchanged and the thrust and tow bar, cool. Find the value of F. Okay, cool. So we have F and A. So what we're going to do here is we're going to need to resolve twice, okay? Because we don't know what f and a are. Now, okay, what if we used our old trick of combining them? Okay, well, the problem with that is if I combine them, I'm still going to have f and a, right? So instead, it actually makes a lot more sense to bear in mind that f only affects the car, right? So if I can work it out for the trailer, I can work out the acceleration straight away. Now, I want to point something out, is that there is nothing wrong with combining them and then resolving one or the other. It's a slightly longer method, but it's not wrong. If I've just used my brain, which I understand might be a bit tricky because you've never done this before, but if I use my head here, I can see that, again, I know that it's going to be accelerating to the left, that if I look at just the trailer, f is not in the equation. The only unknown I'll have is a. So again, let's use f equals ma. That means we have 100 newtons plus 80 newtons is equal to, and the reason why it's plus is because, again, they're acting in the same direction. Okay, so you can basically split this down the middle like this. Okay, equals mass, which is 250 times a. There you go, and we're basically done, right? We're done straight away. 180 over 250. Which is 0.6, actually. You can divide the top and bottom by 50. Good, and you divide that by 1, because 18 over 25. Cool, that works. And, okay. So, what next? Well, we've worked out the acceleration, that's good. But we need to find the value of f. So what we're going to do now is resolve for the car, so this right-hand side, and if you notice, we have everything except f, and we're done. So car, again, we're going to take the right as positive, which means we're actually probably going to get a... Actually, no, we're not. Never mind. Don't listen to me. F equals ma. We have the fact that f minus 80, because it's in the other direction, equals 750 times 0.6. So now f is equal to 750 times 0.6 plus 80. We can work that one out. Oops. Which is 530 newtons, and we are done. Yeah. Which should make sense, right? You want your brakes to have quite a high amount of force. So, let me just verify this. Yeah, it's perfectly fine. So yeah, again, bit tricky, but if you notice in total, these questions have all been like 13 marks in total, which is, it's quite a lot. It's definitely not bad. And it can be very useful to kind of go through these. Hopefully that all makes sense. And again, you can apply a lot of like logic and reasoning in order for your answers. But if not, again, just resolve for everything. Like if you got stuck, I would resolve for the trailer, the car, and then the whole system. And by that point, at the bare minimum, you'll have a simultaneous equation that you can use, right? And that's the most important thing. Is the great thing about mechanics is that, well, not the great thing. In a lot of mechanics questions, you get simultaneous equations. So if you get a simultaneous equation, you shouldn't be surprised and you shouldn't worry about it. It's always going to happen, and you can always work something out from it. Okay. I think that's pretty good for now. So we've done basically every single type of question they can give you. Again, if you would like me to go through more, I'm more than happy to. But for now, I think that would be good enough, and then we can move on to basically the next step of pure.